Hello and welcome to this talk about elementary equivalence versus isomorphism in semiring semantics. I will start by introducing semiring semantics for first-order logic. And in standard semantics, we have a first-order formula and a structure, and we ask whether this formula is true or false in that structure. Now, what we do in semiring semantics is we replace these truth values by arbitrary semiring values. So we use a commutative semiring, and 0 in this semiring represents false, and any non-zero value represents some shade of truth. And now we can apply this to derive more than just true or false from evaluating this formula. If we use the natural numbers, we can count the number of proofs, for example, for this formula and this structure. Or we could use real numbers between 0 and 1 to obtain confidence scores. And we could even use polynomials to obtain provenance information. So we could find out which facts in A are responsible for our formula phi being true. And provenance analysis for logics actually originates from databases. How do semiring semantics work? We observe that a classical structure can be seen as a supply of truth values for all instantiated literals. So for example, if we have a unary relation symbol R and we have two elements A and B, then we could say that the literal RA is true and the literal RB is false, and of course the opposing literals are just flipped. And now this is easy to extend to semirings K, because we can build a K interpretation by taking the same literals, and instead of mapping them to truth values, we map them to values in K. And now this induces a straightforward evaluation strategy for all first order formulas, because we can make use of the semiring operations. For example, we can use the addition to interpret disjunction and the multiplication to interpret conjunctions. And of course, the quantifiers, for example, the existential quantifier on the finite structure, can be seen as a finite disjunction. So we use summation to interpret it as well. And we use multiplication to interpret universal quantifiers. Now, for example, if we wanted to interpret the formula RA or not RB under some K interpretation, then we would get the value that the literal RA is mapped to plus the value that not RB is mapped to as our final result. We would like to understand the model theory of semiring semantics, and we start by lifting classical notions from structures to K interpretations. And first of all, we start with isomorphism, and we say that two K interpretations are isomorphic if they are the same up to renaming. Now this is very similar to the classical case. And as for elementary equivalence, we say that two K interpretations are elementarily equivalent if they agree on all first order sentences, meaning that if we interpret these first order sentences, we get the same value. Now we have to be a little bit careful about this compared to classical semantics, because we cannot speak of satisfying a first order sentence since there are more than two values, like more than the values true and false. With these definitions, we see that some classical results easily lift to semiring semantics. For example, the isomorphism lemma lifts to semiring semantics. So if two K interpretations are isomorphic, they are also elementarily equivalent. This is not very surprising, and it's also desirable because we want our logic to be invariant under renaming. Now we could ask whether the converse holds as well, at least for finite K interpretations. So if two finite K interpretations are elementarily equivalent, does that mean that they must be isomorphic? Now, we know that for classical structures this holds for finite structures, because we can axiomatize them with one sentence. So basically we could also equivalently ask for K interpretations whether there is a set of axioms so that our K interpretation pi A is axiomatized by this set, meaning that if some other k-interpretation agrees with pi a on all the axioms from this set, then they must be isomorphic. But we will show actually in this talk that this is not the case. So this result doesn't lift from standard semantics to semiring semantics, and we will see that it doesn't hold, for example, in min-max semirings. However, we will also see that it holds in some semirings. So in the Viterbi semiring for confidence scores, we can actually build an axiom system for each Viterbi interpretation. However, we can even ask more questions. So for example, even if we are able to find a set of axioms that characterizes our k-interpretation, can we do it with a finite set of axioms? And can we do it with a single sentence? Perhaps surprisingly, these two are not equivalent in semirings, as we will see, because we cannot simply take a finite set of axioms and set the sentence to be its conjunction, because as you know, conjunction is interpreted in terms of a product, and from a product we cannot always infer the values of all its factors. Before proving the results, let's show an example. So we use a first order formula, and as our semiring, we will use the Viterbi semiring. So the elements of the Viterbi semiring are real numbers between 0 and 1, and they model confidence scores. The addition is the maximum, and the multiplication is as usual. So if we have a Viterbi interpretation, for example this one, we could see it as confidence scores for all the literals. So our confidence that the literal RA is true is 0.9, and our confidence that not RB is true is 0.5. And now by applying semiring semantics to this formula with this interpretation, we can find out the confidence that this formula is true. And this is 0.9 because we have a disjunction here, and this disjunction is interpreted as maximum in the Viterbi semiring, which depending on the application, of course, one could say it makes sense because we have an alternative here. So our confidence that at least one of these formulas here holds is, or at least one of these literals holds actually, is 0.9. So this is our confidence score for phi AB. In fact, there are many more applications of semiring semantics, and our work is actually part of a larger project devoted to understanding semiring semantics and even extending it to various logics. So for example, if we had a logic that is strong enough to express reachability, we could even find shortest paths by evaluating a suitable formula in a suitable semiring. So even this problem could be expressed as a semiring interpretation. Now let's get back to our questions, and we will focus specifically on the first question: does elementary equivalence imply isomorphism? And we will see that this is not the case. And for that we will construct a counterexample in a min-max semiring. And for now we will assume our min-max semiring has at least 4 elements. So basically a min-max semiring is basically just elements from 0 to n, and the addition is max and the multiplication is min. So this is a very simple semiring. And our counterexample looks as follows. Here I will explain the notation. So this is the universe of these two k-interpretations, and these are unary relation symbols. So the cells in the table basically represent the values. So this 1 is the value assigned to the literal PA. And now, what is the observation here? The first observation is that these two k-interpretations are not isomorphic. In fact, even if we try to apply the Ehrenfeucht-Frisé games from classical semantics, if we try to extend them to semiring semantics, we would see that the spoiler would win in one term, because for any element that you pick in any of these structures, there is no corresponding element in the other structure. For example, if we pick A here, then we have PA mapped to 1, QA mapped to 3, but there is no such element in the other structure. So in fact, the spoiler would win in one turn, which would mean that if the Ehrenfeucht-Frisé method still works for semiring semantics, then there would have to be a formula with quantifier rank 1 that separates these two structures. But we will show that this is not the case, and that these structures are actually elementarily equivalent, and there is no first order sentence separating them. But we do not have any methods to prove it, because normally, if we were in classical semantics, we want to prove that two structures are elementarily equivalent. A very straightforward way to do that would be using Ehrenfeucht-Frisé games. But as you see, the Ehrenfeucht-Frisé game would tell us that we can separate these two structures. So in order to prove that we cannot separate these two k-interpretations, we need to take a detour via semiring homomorphisms and split up our min-max semiring. So what we do is we define 3 homomorphisms, and the first one, H1, basically maps 0 to false and all other values to true. And the second one splits our min-max semiring down the middle. And the third one splits our semiring here. So basically it maps 3 to true and all other semiring values to false. Now, what do we obtain here? We see that our set S separates our semiring in the sense that if we have 2 distinct elements from our semiring, then there is at least one homomorphism in this set that separates these 2 elements. So you could see it as a sort of injectivity, but of course injectivity only applies to one function, but here we have a set of homomorphisms. So at least one of them separates these 2 values. And thanks to this property, we have the following theorem. If we have such a set of homomorphisms that separates K, and we have 2 K interpretations, such that applying any of these homomorphisms to these K interpretations yields elementarily equivalent interpretations, then it must mean that the original interpretations are elementarily equivalent as well. This is exactly the tool that we need in order to prove that our counterexample from before is correct. So we simply take the separating set of homomorphisms, and we apply them to our counterexample all in order and verify that the resulting interpretations are all elementarily equivalent. So we can do that. This is the first homomorphism applied, this is the second one, and this is the third. And we see that each time we end up with isomorphic interpretations. So in this case, it's the same interpretation. If we apply H2, then we can show with this isomorphism that the resulting interpretations are isomorphic. And in the case of H3, we need a different isomorphism, but still we end up with the same result. So applying all of these homomorphisms yields isomorphic interpretations. And by the theorem from the previous slide, we conclude that our counterexample is actually correct. Hence, our 2 interpretations are elementarily equivalent but not isomorphic, which of course answers all of our questions negatively, because it means that we cannot hope to axiomatize finite K interpretations if we can find 2 of them that are elementarily equivalent but not isomorphic. However, we will show that there are semirings where elementary equivalence does imply isomorphism. And in order to show that, we will draw inspiration from the classical case, where we know that elementary equivalence implies isomorphism, because we can take a structure, a finite structure, and maybe the same structure with renamed elements, so an isomorphic structure to show the example. And now we can attempt to characterize A with a characteristic sentence. So this sentence should have the property that any other structure satisfying it must be isomorphic to A. And we can do this by introducing variables for the elements of A, which is always possible as long as we have a finite structure. And then in this part of the formula, we assert that these elements are all distinct and there are no more elements. So this part is not very interesting. We will call it phi x from now on. But the interesting part is the part with the literals, and here we can just enumerate all the true literals that we want. So for example, we want x1 to correspond to v1, and because p holds in v1, we write px1. And if we want x2 to correspond to v2, we do not want p to hold in v2, so we say not px2. And if we do this for all literals, then we can completely characterize A up to isomorphism. Now we try to move this approach to the Viterbi semiring. So we have two isomorphic Viterbi interpretations, and we will try to characterize pi using the same approach from before. So we construct the same characteristic sentence, and we observe that it does not work anymore because we can simply swap these two values here. And for example, we put 0.9 here and 1 here. And what happens is this breaks our isomorphism, but since these conjunctions are interpreted by multiplication, it doesn't actually change the value of if we interpret the characteristic sentence under this new swapped structure. So the old characteristic sentences do not work anymore, and this is because we cannot separate the contributions of each individual literal to this product. We solve this problem by repeating each literal a varying amount of times. So we sort them by their value, so this is the smallest one, and we repeat it only once. So we write px3. This is 1. And then the second smallest one is repeated many times, say 10 times. So we write not px2 and not px2. So repeating means we just use a conjunction and repeat the same literal in this conjunction. And the next literal is repeated even more, so say 100 times. Now, if we do that, we have ensured that we cannot swap these two values without changing the evaluation of the characteristic sentence. So we are safe from that. However, there is one problem. No matter how many times we repeat these literals, we can always find a very small epsilon, so that if we decrease this value slightly by epsilon and increase this value to compensate, say by epsilon or epsilon divided by 3, we may end up with the same value of the characteristic sentence even if we break the isomorphism. However, in order to compensate that, instead of using a single characteristic sentence, we take the set of all characteristic sentences for all epsilon. And if pi prime agrees with pi on all these characteristic sentences for each epsilon, then we know that pi and pi prime have to be isomorphic. So this is how we axiomatize Viterbi interpretations, at least finite Viterbi interpretations, up to isomorphism. Hence, for Viterbi interpretations, we can immediately answer the first two questions with yes, since we have found a system of axioms that characterizes one Viterbi interpretation up to isomorphism. But with a little more work, we didn't show it here, but with a little more work, we can even build a finite system of axioms that does the trick. Like I hinted in the beginning, curiously, it's not possible to do it with a single sentence. So with a little linear algebra, we can prove that a single sentence never suffices to characterize a Viterbi interpretation. Now we have two results, but we would like to know for which semirings K does elementary equivalence imply isomorphism for finite K interpretations. So basically, we would like to obtain a classification. And I will briefly talk about the approach to get such a classification. In order to do that, we can look at polynomial semirings and try to find counterexamples there. Because if we can find a counterexample with polynomials, then we may try to extend or to lift this counterexample to all semirings by simply plugging in values into the variables of these polynomials. Or we could take a more restricted class of polynomials, for example, polynomials without coefficients or with Boolean coefficients, and we could use these polynomials to make some statements about idempotent semirings, because these polynomials actually capture the idempotent semirings. So in general, we try to construct counterexamples on polynomial semirings, and these examples may carry over to an entire class of semirings if we manage to find them. Now, to close the talk, I will summarize our results. So obviously the answer is no to all of our questions in general, because we have a counterexample. But if we split it by the semirings, then the situation might be different. For example, the Boolean semiring, this is the classical case, the answer to all 4 questions is yes. And these are the results shown in this talk. So as you see, for the Viterbi semiring, also the answer to most questions is yes. What we've also tried to do is find counterexamples on the polynomial semiring, but we have found that this is impossible, that we could actually axiomatize nx interpretations up to isomorphism, at least finite nx interpretations. We do not know whether there is a finite axiomatization or not, so this is still open. However, we have managed to use weaker polynomial semirings, such as, for example, polynomial semirings without coefficients or with Boolean coefficients, and in some cases we have managed to lift these results from weaker polynomial semirings to an entire class of semirings. And this is how we obtain some more general results in our paper. Now, as an outlook, we would like, of course, to obtain a complete characterization of where these questions hold and where they do not hold. And also, what we're interested in is we would like to adapt Ehrenfeucht-Frisé games to the semiring setting. And as you have seen before, if we try to do it in a naive way, in the obvious way, it doesn't work. So we are trying to adapt it, but so far it has proved to be very difficult to move Ehrenfeucht-Frisé games to the semiring setting, and we are hoping to solve this in the future. Thank you for your attention.